Our final presentation today is from my co-chairman, Todd Bridges, who's the senior research scientist, and you already know all about Todd, so I won't go through his bio. But he's going to talk to us about use of climate scenarios in assessing risks and deciding on adaptation measures. Todd.
Yes. So good afternoon to everyone. I changed the title just a little bit, but it's the same general topic of assessing risks as well as assessing adaptation measures with respect to climate change. And I thought it would be useful just to get oriented around the concept of resilience. I'm aware that there are dozens and dozens and dozens of papers published in the literature defining resilience in different contexts, but this relatively simple graphical representation I think is useful to show how that we can apply these concepts of preparing, resisting, recovering, and adapting, which are, essential qualities of the resilience paradigm. If we have some system that we want to protect, say a navigation system, we can take preparatory steps for some disturbance, whether it be a storm. We can assemble the engineering such that it resists the potential for some damage or loss in function. We'd also like to configure the system in a fashion that minimizes the amount of effort that needs to be invested to recover that system, to gain back that function, and then ultimately adapt the system such that the next time a disturbance of that same type occurs, maybe we suffer less loss of function, right? That's ideally what we might like to achieve. There we go. And the idea is that there are domains to this concept of resilience, even if we're thinking about it in terms of navigation infrastructure. We have what we build, okay, the physical structure itself, but then we have the environment within which that structure exists. And then we have the community that surrounds and supplies and is served by that infrastructure. So it's really three components that we need to concern ourselves with. It's not simply the physical infrastructure itself. And that infrastructure provides a range of services. And this is just a map that shows the movement by tonnage of freight in the United States through different corridors, including rail, highway, and the blue line is inland navigation. Obviously, it's an intermodal system. And then that infrastructure, this system of three parts is going to be affected by disturbances of a range of types. And this is what a levee looks like when it's being overtopped by water during Hurricane Katrina. So in the context of this discussion of resilience and this social, environmental, and engineering system, we can think of climate change adaptation in a number of ways. I'm just going to emphasize three with a simple case study, maybe not so simple, but we have threat combinations. These things don't come at us one at a time, these threats and these drivers. The case example I'm going to show you in most detail is sea level rise in combination with coastal storms. That is, storms riding on higher water levels. The scope of the analysis, Adam emphasized that we can have different levels of analysis. I'm going to show you a very highly resolved scope of analysis for a very important system. And then integrated solutions. How do we put together solutions in an integrated way to address this three-part system? So we've already seen different representations of this issue, that the surface of the planet is warming. The data are quite clear on this point, and there are a range of consequences associated with that warming, including those that affect our navigation infrastructure. We have a variety of threats around the world, including the type of storms that we have to be concerned with in the United States, very large hurricanes, this one affecting most of the eastern seaboard of the United States. Even though most attention was focused in the New York area, there were measured consequences of that storm that went all the way down to the northern part of Florida and all the way up to the Gulf of Maine, so the entire coastline of the East Coast. This is the first and most detailed case study I'm going to show you. several years ago, a team of many engineers and scientists at ERDC focused their attention on assessing the combined, if you will, threat of sea level rise and coastal storms to Naval Station Norfolk. This is the largest naval base in the world at the opening of our Chesapeake Bay. We have over 7 miles of piers and wharfs at this naval base. It serves 75 warships, and there are more than 3,000 ship movements at this naval base every year. These piers that you see represented here have a combined investment value of billions, the piers themselves. So what about climate change in this context? So we looked at and developed a system to analyze the combined threat of sea level rise, different scenarios of sea level rise, and different intensities of storms. But one of the first things that had to be done is to map the infrastructure itself. I think we might be surprised, because it was our experience here, that this needs to be undertaken in the first place, to actually map the infrastructure. But in our experience at this naval base, it didn't reside in a neat binder on a shelf somewhere. These systems are complex, and those who are in the audience who work at and support ports can understand the complexity of the systems that are necessary to feed these piers that serve these ships. And so we had to assemble this system, and we did it in the form of what is called an asset capability network, to understand the connections and the flows and the dependencies that exist in this complex network of infrastructure. That had to be mapped, because then we were going to force wind and water and waves against that infrastructure system. And we had fragility curves to allow us to understand how various components of that network of infrastructure would break or fail, and what the consequences would be of that failure. We deployed a complex system of models in this case to take water and wind up against that infrastructure, and I'm not going to go through this in any detail for sake of time. Maybe just emphasizing the first part in the red block at the top, where we were looking at a range of sea level rise scenarios that went from 0 sea level rise, so the current condition, 0.5 meter, 1 meter, 1.5 meters, and 2 meters of sea level rise. And on those different levels of water, we moved 5 intensities of storm, drawing from an extensive database of such events from the past that is maintained by FEMA. I mean, we also included what we call a nor'easter within that same set that I'm not going to show you here. And so we moved the wind and the waves and the surge against this infrastructure and measured the performance of the system against those conditions. So this next slide, to get you oriented, you can see a 0, 0.5 meter, 1 meter, 1.5 meters, and a 2 meter sea level rise. This is the installation boundary, and these maps show inundation of the surge, where the water is and the depth. The hotter the color, the deeper the water, okay? And so these maps here for different levels of sea level show where the water is for a storm with a 1-year return frequency, okay? And of course, the water does not stop at the boundary of the installation, but that's where we stopped it artificially. The water also goes into the city. But for purposes here, we're just focused on the naval installation itself. So here's for a 1 meter storm, a 1-year return period storm, a 10-year return period, a 50-year return period, and a 100-year return period. So to give you a sense of perspective, this red color here, we've got water as deep as 9 meters over most of the base. So that's a bad day. That's in fact bad months, right? If you're the admiral that's in charge of this naval base, and all of the missions in the Atlantic, the Mediterranean, and the Indian Ocean that originate from this naval base, and it's 75 vessels. And those piers, which you can see, in the diagram here, are basically inundated themselves. So what do we do about that? Well, one of the things we want to know about tipping points, right? Where things go from relatively inconvenient or a nuisance of maybe hours to a few days of disruption in service to months or catastrophe, right? And so the team developed, in essence, an index to measure mission performance, the outputs from this infrastructure. And you can see it here from a 0 to 1 scale. And this is just looking at 3 piers, 11, 12, and 14, on these lines. And what you can see here is that when you go from about a half a meter to a meter of sea level rise, things go from relatively inconvenient to pretty much catastrophic in terms of the service rendered by that infrastructure. And the team can go in and tease apart what parts of the system, which components are failing and are responsible for these issues, so that the engineering team is in a position then to identify solutions that could address the problem. I want to give you just a quick 2 other examples of work that we've done for, again, military kinds of applications, but they're germane to this case. This was a study that I led that was developing a system of models and data. These analyses, when you need detailed information, are complex. And I'm not going to get into the details of this, but this was a study that we did for Fort Stewart, which is in the state of Georgia in the southeast Atlantic area. This is Fort Stewart right here. This is a large place. It's the largest Army installation in the eastern United States, that is east of the Mississippi River. It's over 1,000 square kilometers, okay? Very complex hydrology at this site. They are subject to periodic flooding even now. And we deployed a large hydrologic model. In fact, it was the largest deployment of this model in its history. It was 45 million cells within this model. So it took a lot of horsepower to do that. But because of the complexity of the site, we needed to deploy a model with that sort of resolution to get any kind of useful information for where the water was going to be and what inconveniences it produced. Another study that was conducted by us, supported by the Department of Defense, was looking at a different problem. For this case, it was Eglin Air Force Base, which is on our Gulf Coast of the United States, and it was focused on birds, threatened and endangered birds, snowy plover, piping plover, and red knot. And why is the Department of Defense concerned about climate change impacts to 3 threatened and endangered birds? Well, these birds and their presence on the property of this base create restrictions on our ability to train on our land. And so inconveniences to these birds are going to become inconveniences to us in our ability to use the land for training purposes. So how to inform conservation strategies for these birds in view of climate change is important to the Department of Defense, so that we can develop approaches and solutions that minimize the inconvenience that that mitigation creates for us. Of course, we care about birds too, but mission impacts are central to our role. And I'm going to end with going on solutions in my remaining minute and a half, that partnering with nature to adapt and achieve resilience. And this gets to the solutions part that's going to be a subject for tomorrow. But what opportunities are there to achieve better alignment between our natural and engineered systems, and can we, through better alignment, produce better adaptation in view of climate change? I think we can. We have implemented the working with nature philosophy on a large scale within the Corps of Engineers, including for flood risk management, including at the types of facilities that I showed you previously through this Engineering with Nature program. And we implemented these kinds of approaches in the work that we did following the North Atlantic Coast Comprehensive Study analysis that was done after Hurricane Sandy, and developed a report that you can get on the use of natural and nature-based features to support flood risk reduction and coastal resilience. These are the kinds of features, wetlands and reefs and such, that we are seeking ways to integrate with conventional infrastructure to achieve better adaptation. A lot of work going on demonstrating these approaches, for example, here in coastal New Jersey, raising elevations in the Back Bay through restoration of features. There are a number of science and engineering steps that need to be followed in order, I think, to make progress in how to develop these more integrated infrastructure systems, and maybe we'll have some time to discuss these opportunities in the future. I've used this story recently in Rio, but this guy here his name is Thaddeus Koschescu, and he was an engineer that came over to help the young Americans defeat the British. He came over in 1776, and a very talented engineer. And he was developing defenses for battles, including this battle at Saratoga, and you see the landscape for this battle here. And he selected this site and informed the general that this was the best place to confront the British, and he did at this place. And the general, many years later, his name Horatio Gates, was writing a letter to a friend, Benjamin Rush, and he said this about that engineer. He said, "The great tacticians of the campaign were the hills and forests which a young Polish engineer was skillful enough to select for my encampment." And this is an example of, nature being the engineer's partner, right? In this case, to hold back the red wave of the British Army, right? But we could see this application in using landscapes to adapt to climate change in the future. So with that, I conclude, and thank you for your time. And an extra minute, I'm done. Thank you.